We would like to find the potential for f of xy equal to cosine x plus y comma x plus e to the y. Okay, so in general, we should remember here that in order to find a potential for a conservative vector field PQ, so being conservative means, of course, that P sub y is equal to Q sub x without that being a sufficient condition for a vector field to be conservative. But if a vector field is defined over all of R squared, then that turns out to be sufficient. So you start by finding a first, how should I put it, version of the potential where not everything is determined by taking the integral of the first component, let's say, with respect to x. We could also take the integral of the second component with respect to y, but here we're going to find something plus a constant, something that depends on x and y, plus a constant that, unlike integration in one variable where we put plus c, here we will put plus g of y, because things that depend upon y are also constant with respect to x. So then the question is, what should that g of y be? And it will be determined by the requirement that if you take the partial derivative with respect to y of what you found, then that should be equal to q. Okay, so that's pretty much the idea. Let's try to implement it now. So we will start by pretty much arguing that phi of xy, the potential that we're looking for, will be the integral of cosine x plus y dx. And of course, that is going to give us sine x plus yx plus g of y. So now we would like to take the partial derivative of this. And that should be equal to x plus e to the y. So on the left, we get x plus g prime of y, and that should be equal to x plus e to the y, which means that g prime of y should be equal to e to the y, and g of y can be chosen to be e to the y. You could add any constant you like here, but the bottom line is that the following potential works out. We can always verify it, but it's quite simple to see that this simply works out in the sense that its gradient is equal to the vector field that was given to us in the beginning.